Welcome everybody. Welcome, of course, to the University of Sydney and particular to this Sydney Ideas event. As you know, it's just part of the Sydney Science Festival of National Science Week, which is coming to an end. Oh, you have to say. So my name is Frans van Straten. I'm the head of School of Psychology, and I'm also a professor of psychology in our school. And I'm your host for this evening. So our speaker of tonight doesn't need all that much introduction, because I think most of you know him. He's very famous. He's a polymath with a wide range of interests, and I mean really wide. It's from physics and neuroscience to artificial intelligence and philosophy. He's an honorary associate of our university's Department of Philosophy. Among other things, he teaches a course at the University Center for Continuing Education with the title Philosophy for Science, not philosophy of science, but philosophy for science, very important, making sense of the physical world. I have to do that course one day. And if you think that's already exciting, you must be super excited by the title of his presentation of today, which is Scientists and Philosophers Need to Talk. So please join me in welcoming our speaker, Tibor Molnar.
Thanks, Frans. Okay, so, welcome everyone to the hallowed halls of Sydney University. This hall is about 100 years old. It's a little bit more hallowed than most, as you can tell from the luxuriant seating that you'll get to enjoy. The thesis for today's talk is that scientists and philosophers need to talk. Now, that's going to give away my position. You now know what I'm going to say. But before we go there, what I'd like to do is start with a plebiscite. It's all the rage. Everybody's doing it. You don't have to be afraid. It's not legally binding. The Parliament's not listening. It's perfectly okay. Nobody cares. What I'd like to do is I'd like to give you three positions and ask you for your opinion about what you think about scientists and philosophers working together. So the first position is, let's suppose for a minute that scientists and philosophers should leave each other well enough alone. Scientists are doing very nicely, thank you very much. All the technology is flowing. We've got everything from rovers on Mars to mobile phones. The philosophers are contemplating their navels and coming up with how to live the good life, and it's all really good. They shouldn't have anything to do with each other. The other position is the other extreme. They should actually be working very closely together, and maybe the scientists need to consult the philosophers to get them to help them interpret the results of their experiments. The philosophers should consult the scientists to help them with making sense of the world, and so they should work very closely together. And the third position is somewhere in the middle. Who knows what that is? So, show of hands here, who of you think that they should be working very closely together, much more closely than they are now? Wow, it's a huge majority. I'd say about 60–70%. Who thinks they should? Who thinks they should leave each other alone? Almost nobody. And who thinks somewhere in the middle? All right, about maybe 20–30% of you. Okay. Now, who didn't put their hand up? Put your hand up if you didn't put your hand up. Good. You'll need to practice because there'll be more plebiscites later. Okay. So, I'm going to describe, this is the outline for the talk, I'm going to describe to you that there is a bit of a stoush going on between the philosophers and the scientists. They're not really agreeing about something. There's something wrong. And I'll describe the mess that's caused, or maybe the mess has caused the stoush. I'm not sure which. I'll define science and philosophy. I'll tell you what each of them do and what they have in common. I think I'm going to say that what they have in common is that they're both pursuing knowledge of a sort. That might be something they both have to agree to. And then I'll talk to you a little bit about reality, because that's something they disagree about. And then I'll try and wind it up and try and bring the two together and see if I can get them to make friends at the end. And I'll do all that in about, 3 hours, do you think? Okay, so let's start with the stoush. We live in an amazingly complex world. I think that goes without saying. You don't need me to tell you that, and I just did. It's a world that never ceases to surprise us, because things are often not as they seem, right? And sometimes they're really not as they seem, okay? The things are really, but more seriously, it's not as they seem on the large scale, this is Bball 520. It's a galaxy cluster. It's quite a long way away. It's in the tail of the constellation of Orion. You won't see it with the naked eye. It's only got a magnitude 11 or something. There's about 300 galaxies in this. And this is actually 3 photos superimposed one on top of the other. There's a normal visible spectrum that shows you where all the stars and galaxies are. They're all the little dots and the little stretchy bits. You can see some of them are actually quite galaxy-shaped. But then there's 2 other photos. There's one of them which is the orangey, reddy kind of glow. That was taken in the X-ray. That tells us where all the hot hydrogen gas is. So that's where all the... And you'll see that lines up pretty well with where the stars are, okay? But then there's another bit, which is the blue bit. That's where all the gravity is. That's where all the mass is. Now, not even our best theories of dark matter can explain how this system works. We absolutely have no idea. So if you're thinking of a career in astrophysics, the hours are lousy, the conditions are lousy, the pay's lousy, but by God, the work's interesting. Affectionately, this particular galaxy cluster is known as the train wreck, only because we've got absolutely no idea how it works. And on the very small scale, on the quantum scale, this is what a vacuum looks like. Now, I'm sure you all knew that empty space looked like that, didn't you? It's full of surprises. We don't understand how this works. Nobody understands it. But it was presented in the 2004 Nobel Prize when Frank Wilczek got his Nobel Prize. This is what he was talking about. By the way, to give you a sense of scale, the size of this cube is 1 femtometer, which is 10 to the minus 15 meters. Imagine a fraction with 15 zeros along the bottom. That's how small this little box is. And that's what goes on that small scale of the world. So the world is really strange, lots of surprises. And sometimes the reasons are not very obvious. You've got to do an awful lot of work, and we still don't know the answers. Okay, so what do we do as humans? Well, we try to make sense of this complex and surprising world in 2 ways. The first one is we do it empirically. That means we go and have a look. All right? We examine the world much more closely as we can, and we try and reverse engineer the world to say, gee, what must it be doing to be able to produce that effect? Or we might do it rationally. We do it by thinking really hard. We try and concoct a model, a mental model of how we might imagine something doing something that would behave in the way that we observe. So we try and come up with some sort of model. Unsurprisingly, the scientists do the first, the philosophers do the second. Sometimes there's a combination of both. All right, so since the scientific revolution, since Francis Bacon, and who's the father of the scientific method, since around the year 1700, science, which was then called natural philosophy, diverged. The 2 parted company. And the reason is, science became increasingly empirical. They got more and more focused on doing experiments and describing what they see, and the philosophers became more introspective, contemplative, and were thinking more about how the world was built out of how their ideas rather than out of physical bits that the scientists were observing. And by the mid-20th century, they had grown so far apart that they could no longer understand each other. It really got to be that bad. Philosophers now complain that science has lost its grip on reality. I'll give you examples of why they would say that. And scientists charge philosophy with having lost all relevance whatsoever because it's got nothing to do with what they do. So there's actually quite a strong amount of disagreement between them. And in many scientific circles, philosophy now gets some pretty bad press. Here's some examples. Theoretical physicist Richard Feynman, he doesn't need any introduction. He got the 1965 Nobel Prize. He says, philosophers say a great deal about what is absolutely necessary for science, and it is always, as far as one can see, rather naive and probably wrong. Here's a particle physicist, Steven Weinberg, another Nobel Prize winner. He doesn't need any introduction either. He says, a knowledge of philosophy does not seem to be of use to physicists. Always with the exception that the work of some philosophers helps us to avoid the errors of other philosophers. No love lost there, right? Okay? It gets better. Here's more recently, now you all know Lawrence Krauss, he's flavour of the month, he's everywhere on television. He says, the worst part of philosophy is the philosophy of science. It has no impact on physics whatsoever, and so it's really hard to understand what justifies it, because science makes progress and philosophy doesn't. Okay, so he's not a fan of philosophy either. And then even Stephen Hawking chimes in. He writes something like this in the book, The Grand Design, which was co-written by Leonard Mlodinov. He says, philosophy's dead. Well, that's saying it like it is. Philosophy is not kept up with modern developments in science, particularly in physics, and scientists have become the torchbearers of the discovery of the quest for knowledge and, well, bugger the philosophers. Okay, on the other side of the story, in the philosophy corner of this boxing match, the late Paul Feyerabend, for example, he was former professor of philosophy at Berkeley, he said, science has no special features that render it intrinsically superior to other kinds of knowledge, such as ancient myths and voodoo. So he thinks it's no better, science is no better than whatever he does in philosophy. I don't think the philosophy I do is witchcraft and voodoo either, but I don't know but that's what he thinks. But perhaps most vitriolic of all, the most beautiful of all, is Peter Atkins, Emeritus Professor of Chemistry at Oxford. Here he is in 2007 at a conference in University of California, San Diego, speaking on the subject of enlightenment. This was a fabulous conference. Anybody who was anybody was there. Lawrence Krauss was in the audience, Richard Dawkins was in the audience, Daniel Dennett was in the audience, Patricia Churchland was in the audience, you'll get a glimpse of her in the video, Sam Harris was in the audience. These are all, Paul Davies was there. Anybody was anybody was in. This was a fantastic conference, and the whole thing is up on YouTube, so I recommend that you go and find it. Have a look at it. But here he is, and this is what he had to say.
It seems to me that a summary of what the pre-Enlightenment is, or was, really consists of admiration for two types of thought. One, of course, is theology, and the other is philosophy. With I'm sure Dan doesn't mind, but I had to I had to decorate this one to do it. I think if we a symbol for going to Enlightenment 1 is really the destruction of theology and the retention of philosophy, but the replacement, the inclusion now of science as really a principal mode of understanding. And we humans should be enormously proud that we have identified this extremely simple way of understanding the truth about the world. So really, Enlightenment 2, and I had to be rather, let you know that this, although is probably a sunset, I'd like it actually to be a sunrise on civilization. It seems to me that we've got to get rid of philosophy because it really is such a ball and chain on progress.
Cute, huh? Well, that's not the end of it. He goes on.
First of all, you have theology, then you have philosophy, and then you have science. So in other words, theology obfuscates. Philosophy really, I don't know what philosophy does. It interferes with understanding, and science illuminates. And so the sooner we get rid of philosophy is all right at rather a superficial level of human behavior, but it has nothing to say about the fabric of reality, and nothing at all to say about the springs of ethical behavior or anything like that. It really is just a nuisance, whereas science is the only way forward.
Okay, well, it doesn't get any clearer than that, right? Now, in this talk, Professor Atkins makes two claims. The first one is that philosophy has nothing at all to say about the springs of ethical behavior, and the other one is that philosophy has nothing to say about the fabric of reality. Now, as this is Science Week, what I'll do is I'll set the springs of ethical behaviour to one side. That's a whole other talk. I could talk for several hours on that one, so let's put that aside. And let's focus on just his second claim, which is that philosophy has nothing to say about the fabric of reality, because presumably that would be something that scientists might be interested in. So, here's the mess. Peter Atkins insists that science has no need for philosophy, but it seems that scientists do need something. There's something missing, particularly when they try to describe the fabric of reality. Here are some examples. David Deutsch, visiting professor at the University of Oxford, suggests that reality consists of a multiverse of up to 10 to the power 500 weakly interacting parallel universes, not just particles, whole universes all here, all at once, right now, all around you, with additional universes popping into existence at every elementary quantum interaction, which is about 10 to the power 123 times per second. This would have to be the most profligate theory of physics ever invented by anybody. You've got gazillions of universes popping out of absolutely nothing, going absolutely everywhere. I mean, how is this going to be possible? How do we make sense of this? Really, let's get serious here. Meanwhile, Fred Alan Wolf, former professor of physics at San Diego, he says, the reality we observe depends on us, on how we choose to refer to it. Ultimately, reality is a question of self-reference. Well, really? Reality can be whatever you imagine it to be. It's just, if I wanted to make it up as full of angels and hobgoblins, then so it is, that's reality. Surely that can't be right either. He goes on, he says the world we see out there appears in physical form because information from the past and from the future joins for a momentary flash of consciousness. Throw out either the past or the future, and nothing would exist as a solid object. Now, what does that mean? Solid objects made of information coming back from the future? Is that what this stuff is? How do you possibly make sense of that? Do these things make sense? Then there's Stephen Hawking again, his account of the origin of the universe. And this is a direct quote, because there is a law of gravity, the universe can and will create itself out of nothing. Pardon? Does this make sense? How can anything, even a universe, create itself? Okay, it doesn't exist and then it sort of pulls itself up by its own bootstraps. Second, how can anything be created out of nothing? Well, I'm not so sure I can do it. And how can a mathematical law, a regularity that we observe in the world like gravity, how can it cause it all to happen? This doesn't make sense either. And then in 2011, an International Quantum Foundations conference was convened, especially to discuss quantum physics and the nature of reality. Now that's right on game, okay? By the way, it was held at Traunkirchen in Austria. It's an absolutely beautiful place. It's on the bucket list. It's about 75 kilometers east of Salzburg, and you've got to go there, but only when it's not crawling with theoretical physicists. At this conference, one of the delegates was Max Schlosshauer. I hope I got the pronunciation right. And one of the things he did was he surveyed his colleagues, his fellow delegates, and asked them for their opinions, their views on various questions about aspects of quantum mechanics that were not well understood. Questions such as the interpretation of quantum states, quantum indeterminacy, non-locality, superposition, collapsing wave functions, quantum entanglement, all those sorts of things that are really up in the air that we don't know much about. And he also, by the way, asked them to nominate their favourite interpretation of quantum mechanics, of which there are more than one. In fact, the reason he did this is because depending on how you answer these questions, you'll come up with at least one of 14 different interpretations of quantum mechanics. These are 14 different views of reality, all different, and 6 of them have Nobel Prize winners as their champions. So 5 of them can't be right. Think about it, all right? So Max Schlosshauer and others published the results of this survey in a paper in 2013, and here are the results. I'll make that a bit bigger, like so. Here's 13 of the 14 interpretations. You'll notice 2 things. One of them is there's no consensus. The second thing you'll notice is they don't even think one of the interpretations is better than the other half the time. None of them get a 50% vote. The best one is 42% for the Copenhagen interpretation. That was the one Niels Bohr came up with in the early 19-teens. And it's probably the worst one of the lot. The only reason they got the highest vote is because it's the one you get taught first when you come to university. So there's no consensus. It is a mistake, I think, to hold this view that physicists are all agreed about how everything works. No, they don't. They disagree. They fight amongst themselves endlessly. Max asked another question. He asked, how much is the choice of interpretation a matter of personal philosophical prejudice? In other words, is it just whatever you want it to be, or is there some sound reason for why you should prefer one or the other of these interpretations? Only 15% of the people said, no, there's no personal philosophy in this. There's got to be some fact of the matter. The other 85% said, well, yeah, it's more or less whatever you want it to be. So they're not doing physics, they're doing philosophy. And they're not doing it very well, I would argue. So here was the conclusion of this paper by Max Schloss. He says, quantum theory is based on a clear mathematical apparatus, which it is. It has enormous significance for the natural sciences. It enjoys phenomenal predictive success. You wouldn't have laser pointers or DVD players or well, just about anything without it. It's fantastically good. And it plays a critical role in modern technological developments, as we know. Yet, nearly 90 years after the theory's development, there is still no consensus in the scientific community regarding the interpretation of the theory's foundational building blocks. Our poll is an urgent reminder of this peculiar situation. Now, the situation is getting more peculiar every year. What's happening now is particle supersymmetry, one of these ideas that the standard model of elementary particles has a parallel sort of mirror image of another set of particles, and the reality is made up of both of these. This theory's been around for about 25, 30 years. It's in trouble. The LHC has failed to find any of them. And the suggestion is that by now, at the energies that the LHC is currently running at about 13 TeV, that by now they've eliminated just about everywhere where these particles could be. And even if they find something now outside that range, the only kind of supersymmetry theory they're going to come up with is one that doesn't do the work that they need the theory to do anyway, so it still won't work. So supersymmetry is largely dead. And here's an article in Scientific American saying supersymmetry fails the test, physics now has to seek new ideas. So this one is kind of out the window. There's still a few people struggling, hanging on to it, but it's not going to last. String theory is also in trouble. One of its founders, Lee Smolin, wrote a book called The Trouble with Physics, in which he spelt out exactly all the things that were wrong with string theory, like it didn't explain anything, didn't predict anything, couldn't test anything. Why would you bother? It's beautiful mathematics, but so what? And he's given up on it. He's gone back to the Permit Institute, and he's not doing any more string theory. And another colleague of his, a Canadian physicist, Peter Voigt, wrote a book who says, it's not even wrong. It's not that it's either right or wrong. It's not even a theory. There's no way of even thinking that it's wrong. You just can't even do that with it. And then you've got the Big Bang and inflation theory, okay? Now, all the astrophysicists think this is fantastic, and we've got the inflation model and everything works really well. Well, one of the founders is Paul Steinhardt. He was one of the guys who developed inflation theory with 't Hooft and a couple of other people. And he says, scientific ideas should be simple, explanatory, and predictive. Well, you've got to agree with that. And he says, the inflationary multiverse as currently understood appears to have none of these properties. Okay? So he's given up on it, and it's not even scientific, he says. It doesn't predict anything, doesn't explain anything. Well, it's not science. And even Professor Sir Anthony Leggett, a delightful gentleman, I had dinner with him a few years ago, He was here in Australia at the Great Hall, just across the way here, giving the Vice-Chancellor's Distinguished Lecture in 2005, a couple of years after he won his Nobel Prize. And he was saying, in answer to a question in the Q&A at the end of the talk, someone asked him, it should have been me, I should have put my hand up, but I was beaten to the punch. Someone else put their hand up and said, "You must be joking. You can't possibly believe all that." And he turned around and said, "Well, you know, I'm not a betting man, but I wouldn't give it better than a 50-50 chance." And that's a Nobel Prize winner in quantum mechanics. So even they don't believe it. Even they don't understand it or believe it. So clearly the physicists have a problem. Let's acknowledge that, okay? Perhaps what they need is a few philosophers to come along and remind them that things are not always as they appear. All right? Maybe there's more to this than meets the eye. To be fair, the situation on the philosophy side of the debate is actually no less peculiar. We have, for example, David Chalmers. He's at the Australian National University. He's busily spruiking a philosophy of panpsychism, which is a doctrine that all matter, even atoms, have conscious experiences. Now, I ask you, how does the average CO2 molecule feel about global warming? What does that mean? What kind of conscious experience would a carbon atom have? I mean, no idea. John Searle thinks that free will arises from indeterminacy in quantum mechanics. This is a popular view among philosophers. Unfortunately, I have to tell him that this is spherical nonsense. What that means is whichever way you turn it, it still looks like nonsense, okay? The quote comes from Frank Zwicky, an astronomer from the early 20th century, who made that remark about colleagues who were fellow astronomers. He said something very unkind about them spherically. The reason is simple. Indeterminacy, if something doesn't respond to causes, then why would it do what you want it to do? How would you have free will? How would you have agency? How would you cause something to happen if it doesn't respond to causes? It just doesn't work. It's just spherical nonsense. But again, perhaps most peculiar of all are the views of the German idealist philosopher Marcus Gabriel, currently at the University of Bonn. He gave a TED talk not long ago in 2013 in Munich, and this is what he said. I'm not going to preempt it. I'll let him tell you.
I will argue today, in some detail, that there really are unicorns, but that the world does not exist. Okay, so I believe that the world does not exist. But I do believe that unicorns exist.
You heard right. I'm sorry. That's what he said. Now, I ask you, unicorns exist in a world that doesn't? How do you make sense of that? Now, he's written a book about it. Mind you, you can watch the video. It's on the TED website. The audience didn't believe him. He couldn't convince the audience of what he was saying. I read the book, and he couldn't convince me of it. I didn't understand what he was talking about. It's an utter mystery to me. I've got no idea. Perhaps, again, so philosophy's in a spot of bother as well. So perhaps the philosophers need a few scientists to come along and remind them that things are not always as they seem. There's been some suggestion that the guy inside that mask is Marcus Gabriel. All right, so both scientists and philosophers seem to have left even uncommon sense far behind. I mean, this is getting a bit ridiculous, right? So perhaps it's true. Perhaps science has lost its grip on reality. Perhaps philosophy has become irrelevant. Perhaps I and everyone else has completely lost the plot. Perhaps the whole world has gone stark raving mad. I hope that's not the case. There is a glimmer of hope. There are a few scientists, very few, and as I say there, sadly, no philosophers, only a few scientists. There are a few scientists who now realize that they could actually do with some help. For example, here's one, the theoretical physicist Carlo Rovelli. He's now in Marseille. He seems keenly aware that things are not as they appear. He wrote a book with that title. I'm very disappointed. That was going to be the title of my book, and he pitched it. Anyway, here he is at the London School of Economics last year in 2016, delivering a lecture entitled Why Physics Needs Philosophy. I wrote to him after that and had a bit of a chat. It was very good. Anyway, here he is. I'll let him tell you. This is after he gave his talk, and there is a Q&A session at the end, as there will be after this talk. And one of the philosophers in the audience asked him a question.
So thank you for a very interesting and sensitive talk. And I'm now very excited to go back to my armchair and think good thoughts. But now I have a bit of a phobia.
Yeah, that's what these guys do, right? It's a very good but.
Because I want to think of good philosophy, not bad philosophy. And before you come back and tell me that it's my job to define these things, let me tell you a quick story. I listened to Ed Witten give a talk to mathematicians a few years ago. And he had very definite ideas that the mathematicians were all doing bunk and they should listen to him and do what he said so they can do something that will help physics out. Maybe if you can give a more sensitive notion of what good philosophy is, what do you think we should be thinking about? And what sort of questions would make good philosophy rather than bad?
The last thing I want to do is to do what Witten does.
Applause from the right.
But what I wish philosophers of science do, I mean, they certainly are doing. I had a list of questions, a long list of questions. These are questions which have been discussed in the foundations of physics community at large, and I think this is a very relevant question. I would like scientists, philosophers, to help me answer the question: is this viable? So take the confusion of string theory today. Is this viable or what's wrong? Take loop quantum gravity today. There is no space, no time, no this. Does this make sense? You guys are so much better than us physicists in asking the right questions. Look, you're doing that, but there's obviously something wrong. There's obviously something that you're saying one thing, you're using a term in different ways, you're making a set of arguments that don't stay together. So in other words, not just look at non-relativistic quantum mechanics, but also not just look at quantum field theories. Look at quantum gravity, look at the new things, look at inflation, look at pre-Big Bang cosmology. I know that's shaky ground, horrendously shaky ground. So, but maybe some inputs are maybe useful. I don't know. That's one first thing that comes to my mind.
Okay, so Carlo Rovelli asks, are his physical theories viable? Do they make sense? He's not asking physics questions, he's asking philosophical questions. And these are excellent questions, I think, and indeed we may ask ourselves, say, how do we assess the viability of physical theories? How does one do that? Well, here's a hypothesis. To be viable, a physical theory must be somehow realistic, whatever that means. It must be realizable in a way that accords with some sort of a priori conception of reality. We all have a sense of what we expect reality to be, and it sort of has to be how we think a physical world might be or even can be. If I came up with a physical theory that was all full of angels and hobgoblins, you'd say, no, you can't realize a world like that. You can't do it. You can't have it. So it has to be somehow realizable. And this is why Carlo Rovelli needs philosophy. Physical theories must accord with our sense of reality rather than dictate how reality can be. Simply, if I said, my theory has angels in it, and therefore I'm going to dictate that reality must have angels in it, you're going to send me away, or they'll take me away in a little rubber room or something, and say, no, you can't have that. You can't have physics dictating how reality is. We have to have a sense of reality, and we have to check if our physical theories somehow conform or align with that. If someone comes up with nonsense that we can't make sense of, we're not going to say, okay, well then therefore reality is just nonsense. Because then any theory at all is going to be true. All you have to do is declare reality to be whatever the theory requires. There's no way of getting a right theory and a wrong theory, no way of assessing a theory if your theory creates its own assumptions. Theory has to agree with reality and not the other way around. It doesn't work the other way around. And this is precisely why we have a problem. Many features of 20th century physics, in particular of quantum mechanics and general relativity, do not accord with our regular notions of reality. We don't know what wave-particle duality will look like. We don't expect reality to be non-local. We don't expect virtual particles. We don't understand curved space-time or time dilation or parallel universes or superposition. We don't get these things, so reality doesn't seem like that to us. Now, of course, the scientists have observed and measured countless properties and behaviors of real physical phenomena, they say. So they argue quite reasonably that reality simply has to be as those behaviors indicate. They can't be wrong about that. And if that seems counterintuitive to us, then that's too bad for us. Which is fair enough, except for one minor detail, and that's physicists have devised at least 14 different quantum realities, or possibly 10 to the power 500 of them. They have no way of telling which one is the right one, and even if they did, none of them are anything like the way we expect or understand reality. So we can't accommodate any of them. On the other hand, philosophers have been pondering the nature of reality for what seems like an eternity, haven't they? I mean, really. And they too have devised many different models, none of which accord with the physical evidence. So where's the common ground? Here's the problem in a nutshell. Either our physical theories, our interpretations of scientific observations are correct, and our notions of physical reality don't make sense, or our sense of physical reality is correct, and there's something wrong with the way we're theorizing about our scientific observations. Or again, maybe we're thinking about everything the wrong way. This is the famous Duhem-Quine problem. This is well known to philosophers of science because there's no way of telling where the error lies. In principle, there's no way. In our physical theories or in the assumptions on which they're based. One of them has to be wrong, but you can't tell which. All you know is that if you've got these assumptions and these theories, it doesn't work. But which of those two? Well, that's a debate between scientists and philosophers, isn't it? There are two ways to proceed, of course. We can maintain, as scientists do, that our sense of reality must align with our physical theories, or we can maintain, as philosophers do, that our physical theories must align with our sense of reality. Clearly, these two are going to be at loggerheads, and hence the stoush between philosophers and scientists. Perhaps we have to do a bit of both. Well, maybe they're both wrong. Who knows? Whichever path we choose, we need first to formulate a workable definition of reality. You have to have some idea of what the goal is. And it seems that on their own, neither scientists nor philosophers seem able to provide us with such a definition. To understand why, let me try and define for you the roles of science and philosophy. Let's define what they do. So this is what science is, as I understand it. Maybe, how many scientists have we got in the room? How many people with a science background? Slightly less than half. Excellent. And the others are all philosophers, right? Excellent. Right. So, at its simplest, and you can feel free to shout out and disagree with me at this point, science is the quest to answer just one question. What must the world be like in order to produce the phenomena that we observe? Simple question, fiendishly hard to answer, but it's a simple question, right? Isn't that what science is trying to do? In other words, science is the business of trying to work out what's going on. Not easy, but that's all they want. But science is about more than that, I want to argue. It's also about making sense of what you discover. You describe what's going on, but then you want to understand it somehow. You want to work out what's going on. And we expect science to explain the mechanisms and processes that make the world work. We want that kind of explanation from science, not just, this happens, and then that happens, and that happens, and we don't know how, but it doesn't matter. So we want science to describe the fabric of reality. Peter Atkins is right in this. This is something science should do. And yet, despite this, scientists seem very reluctant to discuss reality. They really don't want to go there. Paul Dirac, another Nobel Prize winner, he got the 1933 Nobel Prize. He wrote in 1930 questions about what decides whether the photon does this or that, the other, whatever he's talking about. He says it cannot be investigated by experiment should be regarded as outside the domain of science. So it's not something science should concern itself with. If it can't be checked by experiment, it's not a scientific problem. And here's Professor Garantie Lewis, he's Professor of Astrophysics here at this university. Last year at a meeting, he said this to me on the 29th of February. He said it to me to my face. He said, physics is concerned only with making predictions. We leave worrying about reality to the philosophers. In other words, physics is concerned only with describing the results of experiments. It is not concerned with explaining what's actually going on. That, he says, is a task for philosophy. Well, now we're left with a conundrum, all right? We've got some scientists, Stephen Weinberg, Peter Atkins, and others, who maintain that understanding reality is a job for science rather than for philosophy. And then we've got other scientists like Paul Dirac and Garantie Lewis who say understanding reality is a job for philosophy rather than for science. Well, whose job is it then? To find out, I guess we should have a look and see what philosophy does. So, what is philosophy? Okay, the late Anthony Quinton, an Oxford Don, one-time president of Trinity College, defined philosophy as rationally critical thinking of a more or less systematic kind about the general nature of the world. Oh, harmless enough. So what is critical thinking? Well, I drew a flowchart. If you don't know what to do, draw a flowchart. I'm sorry, my IT background is showing. Here it is. This is what I think thinking is. All right? This is what you and I are doing all the time. We have experiences, we make observations about them, we think about them, we act on how we think, and we have more experiences. We accumulate knowledge, and we act on that and get more experiences. And if we're really lucky, we accumulate some wisdom along the way. And over here on the left, we theorize about what reality is, and we have rules about how we do our thinking and reasoning. We have theories about what truth is and what ways of knowing are, and we have some theories about value and worth and what's worth what. And so that's kind of how it works. In summary, it looks like this. This thinking about the springs of ethical behavior all happen down here. That's the stuff we put to one side, so I won't say any more about that. I'll pretend it's not there. The stuff on the right is thinking about the world. That's where you interact with the world. That's where all the fun, that's all the action is. That's what scientists do. And over here on the left is thinking about thinking. That's what the philosophers do. And in fact, thinking about thinking is the shortest definition of philosophy that Anthony Quinton could come up with, and it's in his book. Thinking critically about thinking is what is called analytic philosophy. Philosophy is critical thinking. Or critical thinking is analytic philosophy, whichever way around you like it. So that's where the philosophy is. Now, what does that tell us? Well, both sides are pursuing knowledge. They're just doing different parts of the work. Making sense is not itself a scientific process. It can't be done empirically. You can't do it by experiment. You can do an experiment and make sense of the results, but you can't do an experiment and make sense of making sense. That doesn't work. You've got to do something else for that. So, making observations is a task for science, while making sense is a task for philosophy. In the pursuit of worldly knowledge, then, conducting experiments and making sense are complementary functions. You need to do both. The pursuit of worldly knowledge is a joint enterprise. It involves analytic philosophy over here on the left, and science and its experimental empirical functions over here on the right. In fact, it's the philosophy that makes the science scientific. It's where the logic, the processes, the systematic understanding is built. It's all built on philosophical axioms of reasoning, theories of truth and ways of knowing. All of that stuff goes into science to make science scientific. And that's partly the reason for the Stache, because both sides claim critical thinking as their own. Scientists claim that science is inherently logical and that logic is a part of science and they don't need philosophers. And the philosophers insist that logic is a part of philosophy. There is a difference. Scientists use logic, philosophers actually study it. So, reality appears to be at the bottom of all this, we have to argue about what reality is. If it's a joint task for both scientists and philosophers, and they working together, it should be relatively easy to define, right? Should have no problem. And in the room right now, we've got people with science and philosophy background. So with your help, I think we can do this. So let's put on our thinking caps. I hope you brought them. And we'll define reality. The American Heritage Dictionary defines reality as a quality or state of being actual or true, the totality of all things possessing actuality and existence and essence, the sum of all that is real and absolute and unchangeable, which is all very well. Now all we have to do is define what we mean by actuality, truth, existence, essence, absolute. That's what a philosopher would do. That's what philosophers do. Guess what? That's not the way to go about it. It's not going to work because you get tangled up in a mess of words and you end up arguing about the words and you end up not knowing anything. So I'm sorry, I'm not here as an apologist for philosophy. Philosophers do some pretty silly stuff too. So let's do it another way. Let's do a little research of our own, we'll do a little critical thinking, and we'll draw a few important distinctions, and we'll see if we can nut out what reality is. Here's a question I'd like to invite you again, another plebiscite, okay? Are rainbows part of reality? Are rainbows real? Who would say yes? Okay, good majority, about 60, 70%. Who would say no? Oh, a mere handful. Okay, all right, good. Okay, well, let's see. No consensus, but that's okay because it's a distinction we have to draw. Okay? I want to draw a distinction between observables, that are things that are observable, things that you can observe, things that are seeable, are visible to you, apparent to you, and beables. That's a word you may not have heard of. It's things that can actually be there rather than just be apparent or visible or observable. The term was coined by John Stuart Bell. He wrote a paper called The Theory of Local Beables. He was working at CERN before the LHC was built in 1975. And of course, correspondingly, we need to also distinguish between unobservables and unbeables. It's obvious what they are. The beable was coined by John Bell. His 1975 paper is now largely forgotten, sadly. It's a very interesting paper. It's not a very good paper, by the way. There's all sorts of errors in it, so I can understand why it's forgotten by the physicists. But he should be remembered for that one term, beable. It's a really useful idea, and it's a nice distinction to draw. And a rainbow is an observable, but it's not a beable. You can't climb up a ladder and unhitch the rainbow from the sky and walk off with it. If you climb up there, you won't even find the rainbow. It's not actually there, but you can see it. So it's an observable, not a beable. Okay, our second distinction has to be between different ways of cleaving the world at its joints. You've got a world out there, you've got to carve it up and say, this is where one thing ends and the next thing begins. This is the edge of the table or the end of the bench, or this is air, and then the air ends and something else begins. You've got to carve the world up. And there's two ways of doing it. You can do it by its constitution, by its particularity or thisness, the substance of what it is. Where substances change, you have a boundary, okay? Or you can do it by function or persistence. There's two different ways of doing it. I'll give you examples. Here's one. The boundary between oil and water is constitutive. The boundary, somewhere along here, is where the water molecules end and the alkane and naphthene molecules begin. It's different stuff, so there's a division. You would cleave the world at that joint and say, well, there's something different over here to something over there. But what about in a glass of ice water, where the water and the ice are both made of H2O molecules? Now you're not cleaving the world at changes of substance, but at changes of behavior. The H2O molecules in the ice cubes are behaving differently to the H2O molecules in the water. And it's where the behaviors change that you cleave the world. That distinction matters, and I'll show you why in just a second. Our third distinction is between beings and doings. Beings are what things are and what makes them what they are, and doings are what things do and what makes them do it. And of course, doings happen when beings do them. All right? It's not a trivial distinction. You may laugh, but you'll see why it's important in a moment. A bolt of lightning is a doing. It's not a being. There's no such thing as a bolt of lightning. It's an event. A thought is also a doing, not a being. You have a thought, but you can't have a thought. You can't walk around with it in your hand. And the correct delineation or identification of boundaries is critical, because it turns out that beings cleave the world at these constitutive or material boundaries, like oil and water, and doings cleave at functional boundaries. And if you get them wrong, then you can't have any coherent formulation of reality. It just doesn't work. You can make an almighty mess of things. And I'm reluctant to say this, but I think in physics there's a number of places where exactly this distinction is made in error. They've got this confused. All right, another question for you. Are waves real? Who thinks waves are real? Oh, again, a vast majority, 80% of it. Who thinks they're not? Who thinks they're not part of reality? Again, a mere handful. All right, well, I have another video for you. This one's from Harvard University. They built this device. It really is just 15 little swings, little swinging balls. They don't touch each other. They just swing. It's just 15 little pendulums. Of course, physicists among you will know that the pendulums with the longer necks, with the longer strings, are going to swing more slowly than the other ones. Watch what happens. Have a look at this. It's really an amazing effect. I almost fell out of my chair when I saw it. I thought, this really tells me something about the world. Watch this carefully and think about what you see. There are all sorts of patterns in there. Spirals and multiple arm swings. Amazing, huh? Okay, so here's the question. Those wavy patterns were clearly observable. We now know what that means. We all saw them. But was there anything actually waving? Were the waves that you saw real? Who thinks they were? Many less of you. Who thinks they weren't? Okay, you see? Not all waves are real. But the answer depends on what you mean by real, I suppose, on the difference between another distinction between phenomena and epiphenomena. So that's another distinction we have to draw. Phenomena are observables that relate to what there is. If you observe something and it's there, then it's a real phenomenon. What if it's something you observe and it isn't there? Then it's an epiphenomenon, okay? And a rainbow is an epiphenomenal observable. We can say that about it. As are mirages, for example. They're epiphenomena. There's no actual pool of water out there. So, in fact, we might wonder if Peter Atkins isn't chasing phantoms, because the so-called physical sciences, physics in particular, they're not about describing reality at all. I think a correct characterization, a more nuanced characterization of what physics is doing, is that it's merely describing the dynamics of patterns in the relationships between epiphenomenal observables. Because they don't know what's really there, all they know is what they can see, And in many cases, how they see it and what they see is epiphenomenal. So, and there are many more distinctions we can draw, okay? We can draw distinctions between what a detection event is, what an observation is, between indeterminacy and indeterminability, another difference, causation, correlation, attribution, description and explanation, two completely different ideas, fact and truth and validity. Truth and validity are two entirely different things. Logical and physical possibility, they are different things. These are all different distinctions that we have to draw. Unfortunately, a 1 hour talk is not enough for me to go through all those. In my class, it takes over 40 hours. But no matter, because we've already done the work. We've done it. We have our definition of reality. Reality is what gives rise to the dynamics of the patterns that are apparent in the relationships between emergent epiphenomenal observables. Now, that's a real mouthful, right? It's not easy to get your head around that, which is why it takes me 40 hours in my classes to do it. But there is a way of formulating a concept of what reality is, and something that if you want your physical theories to conform to it, it's got to conform to what gives rise to these things. We can never observe reality directly. We can only observe its apparent emergent effects. Ours is not a visibig world. It's not what you see is what you get. So what we should do is take our scientific observations seriously, but must be very careful not to take them too literally. We have to think about what it tells us about the world, but it's not telling us what you think it's telling you when you see it. As Benedict Spinoza wrote back in 1665, reality is that which does not depend for its sheer existence on the existence of any other thing. After all, if it did depend on those other things, then it'd be those other things that would be reality and not this one. In that sense, reality is not heritable. It's not transitive. It's not like that exists because this does. That exists, no it doesn't. This exists, and that's just the effect. So it's not transitive in that way. In 1978, Philip Dick, the American journalist and science fiction writer, said, reality is that which, when you stop believing in it, refuses to go away. It's not bad. It makes a salient point, right? Where are all those parallel universes when you're not thinking about them? Okay? In other words, reality is, well, just what is. So reality is something that exists independently in its own right. It's made up of things that just are, things that can simply be. Beables, no less. All right? They're composed of John Bell's elementary beables, their elementary behaviors and interactions, independent and absolutely regardless of whether they are known or even knowable or even observable by us. It's got nothing to do with us. It's not self-reference. It's not whatever we think it is. What we think will determine what we think it is. It's not going to determine what the world is. The remaining distinctions, all the others that I mentioned, reveal that we can in fact say quite a lot about these beables, and so we can say quite a lot about the properties of reality too, about what the world must be like. We can say it's dynamic. How could it not be? We can say it's heterogeneous. How can it not be that? We can say it's of indeterminate dimensionality because we don't know how many dimensions it has. We can say it's corpuscular, it's discrete, it's quantized, it's neither a vacuum nor a plenum, it's countable. The list goes on, all right? I've got dozens of these, all right? I'm not going to list them all. In my course next year, I'm going to have 160 of those items, all of which are characteristics of reality, which are inescapably true. You can't get around them. And any framework, physics or otherwise, that doesn't have these characteristics is simply not a viable description of reality. It's just not going to cut it for someone like Carlo Rovelli. So let's see if we can draw all this together. From these foundational properties, it really is just 2 short steps to come up with a definition of a fabric of reality for someone like Carlo Rovelli. Based on our newfound sense of reality, and I presume you all now have one, we first decide which of our physical theories are plausible and physically viable, and then we draw on those theories to flesh out the fabric of reality. So it's a 2-step process. The first step is philosophical. The second step is empirical. That's what the scientists will do. And it can't be done the other way around. It doesn't work backwards. You can't start by getting your empirical evidence, your physical theories, to define what the fabric of reality is, and then trying to get reality to match. It doesn't work that way. Philosophers are very well equipped to figure out reality. All the philosophers in the room have just done it, right? But they need scientists to help them work out the nature of the fabric. They haven't got the data to work out what the texture of that reality is. On the other hand, scientists are well equipped to work out the fabric, but they need the philosophers to figure out what it is the fabric of. What is the reality of which they are speaking? So, contra Peter Atkins, philosophy actually has, I think, quite a lot to say about the fabric of reality. Not directly about the fabric, but rather about how to make sense of the underlying reality that we are describing the fabric of. It's this making sense that Ravelli craves and that he's going to use to ground and underpin his physical theories. So scientists and philosophers really do need to talk, I will argue. As Albert Einstein almost said, science without philosophy is lame, and philosophy without science is blind. He actually was talking about science and religion, the actual quote, but it works equally well with philosophy. So, this is my research team. I have to end with some acknowledgements. If you don't recognize the faces, there are the names. Everyone has to acknowledge their research team, so these are mine. Here's some credits for the images. Some blatant self-promotion. No talk is ever complete without blatant self-promotion. So if you want to know more about this stuff, you can find me on my website, or you can find me at the Centre for Continuing Education here at Sydney University. I have a lot of people to thank: Sydney University, New South Wales, Sydney Ideas, Science Festival, the ABC, thank you, Jon. Professor Peter Bowman, New South Wales, Peter Cohen on video, Meredith Hall, who's somewhere here sitting around, she's somewhere here, there she is, up the back. Thank you, Meredith. I don't know if Isabel is here from the Sydney Science Festival. She said she was going to come. And of course, Professor Frans Verstraeten, who is my host tonight, thank you. And last of all, thank you to all of you. You've been a wonderful audience. Thank you very much.